So hello students, welcome to Analog Electronic Circuits lecture number 6. Last time we have started with BJT, its types and its construction. Today we will start with the working of, last time I think we have started with the structure of NP and BJT and we have seen the various modes of operation. Today we'll briefly see how does the BJT operate in one of the particular modes. So before going further, let us revise what we have learned last time. So let's consider a PN junction as a device and we have applied a positive and a negative, a battery to it. So this will make the PN junction forward bias, correct? So that means my current versus voltage characteristics will be exponential in nature. Agree? So this is my current ID versus the diode voltage VD. Now since this is exponential in nature, mathematically we should have something like this. The current should be proportional to the exponential of VD. Yes or no? Ideally, mathematically speaking, this is what it means. Because it's an exponential graph. And there is a proper derivation for this which you don't have in your curriculum. So ID comes out to be equal to IS. IS is the reverse saturation current in a diode, the leakage current we call it. Exponential of Vd upon Vt, where Vt is called as a thermal temperature. Vt is Kt by Q. K stands for Boltzmann's constant, T is the temperature and Q is the charge on electron. And this is around 26 millivolt at room temperature. Alright, so what is the key point we learn from here? The key point is this, that ID is proportional to the exponential of Vd. Now a similar PN junction exists in a BJT. So let's revisit the structure of a BJT. No need to draw this PN junction again. This is what you know from your lower semesters. Can we begin with the BJT, NPN BJT? Yeah, let me fit it in the screen. Yeah. So NPN BJT, we will see it's working in forward active mode. What do you mean by forward active mode? Anyone? There are two conditions for the forward active mode. What are the two conditions? Yes, so base emitter junction, I'm writing short form, should be forward bias. FB stands for forward bias. And base collector junction should be reverse bias. Okay, let's check that. So this is my emitter E, capital B is my base, and capital C is my collector. All right. Now between collector, this is my metallurgical junction, base emitter junction. This is my base collector junction. All right. Now since this is a PN junction, as you can see, this is a PN junction, P and N. I'm not shown heavily doped, lightly doped. Emitter is the heavily doped. Base is moderately doped and collector is the lightly doped, we can say. Alright, so this is a PN junction. Okay, whenever P and N junction meet metallurgical junction, there is a depletion layer automatically formed. Yes or no? Because of drift and diffusion of carriers, they balance out and they form a depletion layer. Here it is. Let me highlight it with this green color. This is my depletion layer. Yes or no? And how does depletion layer is formed? Since I've applied a positive to P and negative to N. Alright. So this will make base emitter junction forward bias. This is clear? Base emitter junction, it will make forward bias. Yes or no? So far so good. Now what will happen now? There are plenty of electrons over here. See, there are many electrons which are over here in this region. Here N region, it's very heavily doped. Okay, its concentration in the range of greater than 10 raised to 17 per centimeter cube. All right, so there are plenty of electrons in this region. It is doped with phosphor atom. That means phosphor atom has 5 valence electron, right? 4 are shared with the neighboring silicon, 5th is the valence electron. So under room temperature, all the phosphor atoms are ionized, means they are readily giving the 5th valence electron for conduction. So for every phosphor atom, there is a free electron available. So that's why the N is, the emitter region is very heavily doped. Now where these electrons will go? There are two ways. Either it will go towards the negative side of the battery, which they will not. Why? Because it's a like charge will repel, so they will be pushed over here. All right. Also, since it is a PN junction, the only way to go is towards the base side. All right. So majority of them will go towards the base region. So we say that these electrons are being injected into the base. Is it the right language? Or emitted by the emitter. Emitter, the name emitter has a significance. It's a source of carriers. All right. The electrons from the emitter are emitted or injected into the base terminal, or injected into the base region. Now base region. Now let's come to the base region. So what will happen is, as you go on increasing your VBE, let me write somewhere. So uh, as you go on increasing your VBE for more and more forward bias, what should happen? Your current IE should increase exponentially. Is it correct? So the relation, the rough relation between them should be current IE should be proportional to exponential of VBE. I'm not particularly so worried about the constants right now. So there should be exponential release. The more you make it forward bias VBE, the more emitter current will flow and the more number of carriers will be injected into the base terminal. All right. Now let's talk about, so far you have understood? Yeah. So what will happen to this depletion layer? Sorry. Depletion layer will become smaller and smaller as we go on increasing the forward bias VB. All right. Now let's come to the base. Okay. So what is base made up of? So base is made up of what? What do you see over here? Holes. But the base region or the area is very, very small. Okay. And it's not so highly doped as compared to this. Maybe here the doping concentration is around 10 raised to 15 or 14 or even lesser. Around 14 we will write. Less, quite less doping. Okay, moderately doped base region. So what will happen? What will happen when this free electron and hole will combine? They can recombine. Whenever an electron and a hole meet, they recombine. All right. So there are, let's take some numbers. There are 10 lakh electrons moving from the N region to P region. Out of those 10 lakh electrons, let's say there are around 10,000 holes over here in the base region. So out of these, yesterday I've given you know the bucket example. You keep a hole and the water slowly leaks out. The concentration goes on reducing. You understood that concept, right? Slowly, not immediately, but slowly. The concentration, the water level keeps on falling down. So here also, as more and more electrons travel to the base or injected into the base terminal minority carrier concentration is electrons. The minority carrier suddenly becomes very, very high, because you see 10 lakh electrons are moving into the base. So not all of them move together, right? Some of them 10,000 move first. So with that 10,000, some of them recombine with the holes in the base region. So maybe from 10,000, maybe 100 of them recombine with the base. So that recombination happens over here in the base region. Then remaining 9,900 will go where? They'll stand over here at the edge of the base, correct? What is over here? This, what is this? Can you tell me? This I am highlighted. What is this I am marking? Yes, this is base collector depletion layer. Can you tell me why it is wider than this? This is quite small, right? The green color one, it's quite small, and this width is very high and greater than that. Why so? Because base collector junction is reverse bias. How it is reverse bias? Let's see. So N is connected to positive, and this negative is connected to positive. So it's reverse bias. Yes. And what do we know about the reverse bias PN junction? As we go on increasing the voltage, its depletion region becomes wider and wider. So it's like it's building an insulator within it. So no current flows. But here something strange happens. So you agree that base collector junction is reverse bias over here. That's why the width is higher. One more thing happens which you should know carefully. Whenever the PN junction is in reverse bias, the electric field across it is very, very powerful. How is the electric field directed over here? This is the electric field. It's very, very powerful. First of all, the reverse bias voltage is higher. Secondly, the electric field is powerful with the applied voltage increasing. All right, because electric field is voltage upon length. Yes or no? So as you increase the voltage, the electric field will increase. So electric field is very, very high. What did I tell you about electrons and electric field? The electrons will always try to run away from the electric field. So These electrons, some of them will, I told you, 10 lakh electrons traveling into the base, not all of them together, but patches in patches. Okay. So 10,000 first batch came, 100 of them recombined with the holes, other 990, where they will go? Should they go into the collector terminal or should all of them recombine in the base? Base region is very, very small. All right. So by the time they recombine, another batch 10,000 comes. Yes or no? So it's continuous supply injection of electrons from the emitter region, because emitter you're becoming forward bias. And if you make it more forward bias, more of them will come. Some of them are thermally generated because of temperature, because we are raising the potential. So there is slight increase in the temperature. All right. So more and more of these electrons are getting injected into the base terminal. Now where these electrons will go? Will they move back? No, they will not move back. Where they will go? They will be diffusing across, they will diffuse across the base region, and they will be attracted towards the collector. They will be collected at the collector terminal. Now you will say, sir, collector also we have electrons. See, these electrons are quite less. Okay, do you know about something about concentration? Now in this room, you all are around 15 or 20 of you all are sitting. Now suddenly if I, 100 students are sitting over here, we can say the concentration is higher. The faces, the room is entirely filled. First of all, there will be no place to stand also if I fit 100 people over here. Yes or no? Now the room is there, spacious. You all are 15 odd, 20 odd people sitting over here comfortably, right? So here also same thing happening. Base is very, very thin. Collector is very, very large. Now if the same number of people I will take you to the classroom, the class strength will become very, very small, because the classroom is even bigger, wider. Same thing happening with the collector. Collector have even lower concentration of charge carriers, maybe 10 is to 13 per centimeter cube. Now what these electrons will do? All these electrons will be running away from the electric field, right? So they will continue to travel and reach the collector. They are collected at the, we say in the technical language, some of them recombine over here. Some of them recombine. Okay, small percent of which, maybe we can say 95% of the electrons are traveling here, are collected at the collector, and only 5%, less than 5% of them recombine with the holes in the base. So majority of these electrons are joining the electrons of the collector region, and then they are contributing to the collector current. Are you understanding? And why does this happen? Because these electron under the influence of electric field will be swept away. The moment the electron see the electric field, they will be running away from it very, very easily. That we call it swept away. And all these electrons are collected at the collector. Just imagine, just an analogy I'm giving you. A cricket stadium, a pitch. Okay, so batsman is batting, so he's at the emitter, and entire stadium is at the collector, the remaining cricketers. So you're playing in the emitter, and ball, where it goes, either to the ground, right, to the field. So all of them are going towards the collector side. So that is what happens. The collector collects the electrons which are coming from the emitter. So not all of them, because the concentration of charge carriers, electrons in the emitter is so high that they keep on coming. They keep on coming, and a very less percentage of them recombines with the base. Because by the time the electrons travel, the next batch comes, the next batch comes, and continuously this process is going on. So very few percentage of them happens. 5% of them recombine will constitute to base current, which is very, very small. Even actually 5% is even higher, maybe 1 or 2%, and majority of them will go towards the collector. So there are three types of current: emitter current, base current, and collector current. Which is the largest, do you see? Emitter current, because it's rich of very, very heavily doped. Next highest, collector or base? Base is the smallest. Smallest. Base is the smallest, because 5% should be, 5% I told you more. Actually, it is, yeah, I have told you all last time, right? So IC is the next highest and IB is the lowest actually. All right. Okay. So this is how your BJT functions. And here the collector, the current is due to minority charge carriers and majority charge carriers. Why? Because in N region, electrons are majority, but they're traveling in the P region also. There also electrons are there. So current flow is both due to both the charge carriers, electrons and holes. Now, one more thing is there. What about, can there be a situation that these holes from here, which are over here, let me highlight this part. These holes from here can also go back to the emitter. Can this happen? The holes from here can also travel towards, see the holes hai na yahan pe, holes will be attracted towards the negative side of the battery. So maybe a small minute out of 100, maybe 5 or 6 will travel back, but they'll recombine with the electrons over here, but still will contribute the current. So base current is actually two factors. One which is electrons which are recombining with the holes in the base, and second, holes diffusing back to the emitter. So these two factors will contribute, this and this will contribute to the base current. Okay, holes diffusing back to the emitter, or the electrons recombining with the holes in the base region. I'll show you the more clear picture of it. If you want to draw this, you can draw this right now. Yeah. Yeah, it is. Yes, conventional current is opposite to the flow of electrons. So if the electrons are going into the emitter, the current will be measured out of it. Yes or no? You're like this. Emitter current will be outside. What about the base current? This is electric field. Huh? This is not emitter, electric field. What about the base current? We'll discuss where it will, whether they will go into the terminal or outside the terminal. What do you think? Into the terminal. And what about the collector current? Leaving or entering? Leaving. So these electrons are going towards the collector region. Opposite direction, right? So the current will be like this, right? Okay, fine. You want to draw or write something, you can. I'll give you around a minute or so. If you want to ask anything, you can ask. I'll give you the textbook version of it also. There is a picture of textbook version wherein you can also draw it. So there are few electrons over here. Let me complete this picture. Here you can see they are more spacious. I'm just giving an illustration. And here there are holes, few of them. Okay. Someone has turned off the air AC. Here it is. Can you just take it and turn it on again? That also. That's what we are going to discuss. Keep it there only. It's on. Yeah. So collector terminal will be inside. Emitter terminal will be outside, right? Leaving. And what about the base current? Leaving or entering? It enters. Yes. This is IB. We'll justify the direction. Just wait. All right. Let us develop. I'll make you all write statements about the base current, emitter current, and the collector current. Don't worry, along with the relations. But here we are trying to understand from the design perspective why this emitter is heavily doped, why the doping of the base is light. comparatively. Why the base is so thin? So this base width, we can call this as, let me show by dotted line, WB. W stands for width and B stands for base width. All right. And here the carrier concentration, let is called as Ne. Ne. Here it will be N or P. N, we can call it N over here. Carriers, concentration of carriers will be NB. And here the concentration of carriers is NC. Suffix E, B and C stands for emitter base collector. N is concentration of charge carriers. Remember that. Okay. N and P, N is made up of N emitter and N collector are made up of four phosphorus dope, are made up of group 5 elements, and P is P silicon, right? P type silicon is boron doped, group 3 elements. So it's a donor and acceptor. So instead of writing donor and acceptor, I'm writing Ne, Nb and Nc. Alright. Now we'll justify this further. Are you all ready now? Okay. So again, a leap of faith you have to take. I'm writing one equation. You have to believe that it might be true, and based on that we'll analyze. If I want to increase the current in the, in this structure, BJT structure, how will I do that? Now, how do you achieve control? How it is better than this diode? See, diode, the problem was it either turns on or turns off. That's it. We cannot control it further. Here we can moderate that. Here, what is the control? The base current is the control. The collector current which is flowing, actually what happens in BJTs, it's called as a current control device. The current flow in this device and across the one terminal is controlled by the voltage at the other two terminals. So basically IC is controlled by voltage VBE. Yes, now if your IC can change due to a voltage VB. Let's see how that relation has come. So let us write one equation. All of you have drawn this? Yeah, written Na. We have understood what is Ne, Nb and Nc. Carrier concentration in N, P and N regions. Alright. So write one equation. This is NPN BJT operation in forward active mode. This is NPN BJT operation in forward active mode. We can have operation in cutoff and saturation also, but this is the most used operating region which we are analyzing. Cutoff and saturation is for as a switch. We don't want to use as a switch right now currently. We want for an amplifier. For an amplifier, this is the explanation we have. And if I want to change it to PNP, then here a majority carrier flowing will be current electrons. There it will be holes. Just replace electrons with holes and the biasing polarity will be different. All the current directions will be different. All the biasing directions will be reversed, and instead of majority carriers as electrons, we have majority carriers as holes. I'll show you the structure, don't worry. So write down the first equation. First of all, IC collector current is approximately equal to IS times, IS is the leakage current, same as a PN junction, exponential of VB upon VT. Isn't it the same formula as a PN junction, right? Yeah, you can see the correlation between this formula and this formula. Almost same. Alright. IC is approximately proportional to IS. So we can say IC, the collector current, is a function of base to emitter voltage. Yes or no? This is very, very important. Collector current is a function of base to emitter voltage. This is called as transistor action. Meaning current at one terminal is controlling, the voltage at two terminal is controlling the current at the other terminal. So that's why three terminals. One terminal is used for control. Sorry, transistor action. Actually, there is a story behind why the name transistor also. We'll talk about that. Okay. Now, this IS is called as reverse saturation current. Let's write down its formula, which is not there for you all. This just only I am asking for intuitive knowledge. So IS is the saturation current, right? This IS is, let me take it up, saturation current. Okay, and it is given by the formula IS is equal to AE. A stands for cross-sectional area. It's a 2D device, huh? It's not a 1D. I have drawn it like this. It's a two-dimensional device. Do you understand 2D? Into the like this. Are you understanding? So it's a cross-sectional area. So AE is the cross-sectional area of the emitter into Q into D NP by dx. Now, what is this? Can you tell me what is this? This is NP is concentration of electrons in P region. So this is called as concentration difference or concentration gradient. Change in concentration versus difference. Yesterday I've drawn one diagram. Now initially the concentration is this much, then it falls down. Correct? Yes or no? So this was the concentration in base. So this is NP versus X. So difference in concentration, because in N region the concentration of electron is so high. In wherever it goes to P region it becomes very very low. So there is a change in concentration. Now this is given by the formula AEQ. This is minority carrier concentration. This is given by, we can prove that Ni square, which is intrinsic carrier concentration, upon Na, which is the base doping, divided by Wb. You don't have the derivation for this, but it's really important to understand from this what we are trying to say. So Is will be given by AEQ Ni square upon Wb Nb. Correct? Why I'm doing all this? I want to increase the current. I want to design this BJT such that my current out of the BJT is very very high. Now how will I do it? How will I increase my current? How to increase current IC? Tell me. One solution will be, see, you will say that, sir, increase VB, but at one point of time you cannot go on increasing VB, right? So VT also is temperature dependent. You cannot control it, right? IS, out of the IS expression, what all things we can do? Do you see we can increase the current IC by, number one, if area of cross sectional is more, right? Matlab, see, I cannot increase VB to very high value. So the next good thing is increase IS. How will I increase IS? If I increase the area of cross sectional of the emitter. Yes or no? It is directly proportional to. So if I increase AE, area of the emitter, then I increase IS. Then secondly, what do I do? Reduce WB. What is WB? The width of the base. That's why the base is very very thin. Did you understand? The smaller the base is, the more less is your recombinations happening in the base terminal, and the more current you can get out of it. Are you understanding? Now third, reduce NB. Correct? That's why you make the doping of Ne very very high compared to NB. Why? Because you want more of them to be injected into the base, not the other way around. Yes, now straightforward, na? This inverse proportional to IS. So if I want to increase the saturation current, I have to increase AE or reduce base width or reduce the doping concentration in the base. That's why emitter is heavily doped. Sometimes they ask you in the question, why emitter is heavily doped? Why the base region is very very thin? Why the doping in the base is less compared to emitter doping? These are all your answers to the same, the various questions, same answer it is. Now, did you understand how to do that? This is doping in the base, huh? Doping in the base region. WB is what? Base width. All right. So this is how you control the narrative. Okay. So what was NP? NP was electron concentration in P silicon. Yes or no? Minority carrier electron concentration in P silicon, that is base. And Ni, anyone knows Ni what it is? Intrinsic carrier concentration. Alright, can we proceed ahead? Yeah. Now I'll show you the actual picture, the diagrammatical picture which we have in our distinct curriculum. This is how they put it. This is there in your textbooks, Dolan Lehman. So forward bias, forward bias. Here now they have not shown the proper symmetry. That emitter is very heavily doped, then base is very thin, and collector is very large. They have not shown that. That's why I've drawn it separately. Okay, but this injected electrons, as long as they are an emitter, they are injected electrons, then diffused electrons, then we have collected electrons. This combination is IC. IE is this total. So some of them, I told you, some of them holes are injected back to the emitter, that is IB1. And some of the holes are recombined with the electrons, that is IB2. All right. So write down what is IB1 and IB2. You can write it down over here. IB1 base current is consist of two components. Can you view what I'm writing? Yeah. IB1 and IB2. What is IB1? Holes diffusing in emitter. Okay. Holes diffusing in emitter or back in emitter. Is IB1 proportional to VB upon VT? It's exponential of VB upon VT? Yes, definitely it depends upon that. What about IB2? Holes recombining in the base with electrons. Holes which are recombining in base region with electrons. Are both of them contributing to the base current? Yes. So actually base current is IB1 plus IB2. But its value is very, very small. Because by the time the electrons comes, the base region is very, very small. So it passes away. And majority of the injected electrons goes to the collector region. And just now we have seen that to increase the current, what happens? What we should do? We should reduce the doping in the base. We should make it very, very thin. So that the current will increase a lot. All right. Now, I'll make you all write proper definitions of emitter current, base current, and collector current, more details. But before that, I want to establish certain things. So write down. This you have understood base two components, IB1 and IB2. This is a diagrammatic picture, but this is not correct picture. As I told you, the collector is the largest. Okay, base is very, very thin. And this emitter region, we can show it like this. But this if you can show collector region a little elongated, then it will be correct. All right. Now see the direction of the currents. Emitter is going out here. Base region is in, and collector is also in. All right. This is in. This is the current flow in an NPN transistor in active mode. Current flow in an NPN transistor in active mode. All right. Yeah. Any queries you have? Now let's write down certain things so that the concept becomes concrete. Now there is a relation between the base current and the collector current. So right now you can write down the relation. IB is given by IC upon beta, where beta is greater than 1, very, very much greater than 1. It is called as current gain. Okay. Your beta, if you increase, that will be resulted by decreasing the base width also. Now let's talk about emitter current. What is the emitter current given by? I told you emitter current is greater than collector current, which is greater than base current. These two are in milliamperes. This is in microamperes. It's very, very small, the units. So if I want to write emitter current in a BJT, emitter current is combination of collector current plus base current. Let me give you some realistic numbers. So if this is 1.01 milliamperes, this will be 1 milliampere plus this will be 0.01 milliampere. Did you understand? Small fraction of it, even lesser than that. Got it? So according to this relation, this equation number 1, how can I rewrite this? IE is given by IC plus, no, instead of IB we write IC upon, yeah, a small relationship will derive. Keep on writing. So can I take can I take IC common and can I write it as 1 plus 1 upon beta, which is beta plus 1 upon beta, correct? So IE is actually 1 plus beta upon beta times IC. And this 1 plus beta upon beta is called as alpha. Oh, upon 1 plus beta upon beta is called as 1 upon alpha, which is times IC. So this term is alpha. So what is alpha actually? Can you tell me? Beta upon 1 plus beta. So here alpha is always less than or close to 1. Less than 1. Correct? Because if this is greater than 1, beta upon 1 plus beta will be almost less than 1. It's very, very close to 1, but not. So beta is a number which is around 200 to, I think in a lab also you have measured, na? How much? 340 something. It's very, very high. Whereas alpha will be very, very small, around 0.95 to 1, close to 0.99. So can what I'm doing is I'm establishing a relation between them. So what is the relation between IE and IC? IE is IC upon alpha, or very, you can write it in a crude manner, IC is alpha times IE. Okay, whichever way you want to understand. Got it? Yes or no? Now, what is the relation of IC with VB? IC is given by IS times exponential of VB upon VT, right? So if I want to write IE, then what will I write? This entire expression divided by alpha, correct? Yes, no? See, this is the emitter current expression. Again, dependent upon VB, definitely. And this all is valid only in the forward active region. So basically base current is normally the input side. Base current is very, very small. So if you make a small change in the base current, it will lead to a large change in the collector current. Okay. So you write down small changes in base current will lead to large changes in collector current. So what are these represented by? So it's represented as follows. IB will change to beta times IC, or IC upon what it will change to. Small changes in IB leads to a large change in IC. What is the first relation we wrote? IB is IC upon beta. Correct, na? So IC will be how much? Beta times IB. This is the large change, beta. So since both are current, Beta can be written as IC upon IB. And since it is greater than 1, it is around 300. That means IC should be greater than IB by a large amount. So a small change in input current leads to a large change in output current. This is input current. Huh? This is input current. This is output current. That's why it's called as a current control device. Input current in your lab experiment also, common emitter experiment. If you change your IB, you observed this, huh? If you change your IB to a small amount, your IC changes drastically in milliamperes. If IB you change, let me give you an example. If IB you change from 5 microamperes to 10 microamperes, IC may change by 5 milliampere to maybe 10 milliampere. Very, very high. I mean, I'm just a rough number which I've given you. So this is the change. That's why it's called as a current control device. Current BJT is called as a current control device. It's a BJT. Okay. Write down one statement. This you're talking about the all the currents together. Huh? Very, very important statement. So write down the topic will be currents inside BJT. So this is a part of your working. Write down because of first point, because of the large gradient of concentration of carriers bracket you write from emitter to base. Okay, because of large concentration, large gradient of concentration of carriers. Which carriers I'm talking about? Electrons or holes? Electrons. Array, electrons are majority in N na. When they go into P, they become minority. So हो गया ना large change in concentration. Yes. So because of large change in concentration of carriers, electrons that are injected, electron that are injected from the emitter region, electrons that are injected from the emitter region diffuse across the base, where they are swept. Swept means taken away, forcefully went. They are swept across the base collector, where they are swept across the base collector depletion region by the electric field and are collected in the collector region, creating the collector current. This is the basic operation of BJT currents inside the BJT. So I'm highlighting the important points. Collected in the collector region. All right. Okay. Now we'll formally write one line on each current, and then we'll end for today. Written completed this statement. If they ask you the working of BJT in forward active mode, you have to write this statement. This will and actually just explain everything about what is happening inside whatever I'm trying to explain for half an hour. How does the current enters, carrier enters, how they interact with base, how they are collected at the collector. Very important statements. Currents inside BJT. So let's start with emitter current. Currents inside the BJT. Now let's start with emitter current. Oh, sorry. Write down emitter current. Okay, there is a emitter current. I guess I have to wait a second. I have turn on the slide again. Yeah, emitter current IE. The current flow. Write down under this. The current flow. The current that flows. Sorry. The current that flows across the base emitter junction is emitter current. Direction of IE is out of the emitter terminal, correct? And IE is dominated by इलेक्ट्रॉन कंपोनेंट. हाँ, होल कंपोनेंट भी है, इलेक्ट्रॉन कंपोनेंट भी है. So IE is actually IC plus IB. All right, is the dominant current. Okay, how it is related by, how can you write the equation? IE is equal to IS by alpha, correct na? Into exponential of नहीं, dominant by electron component. IE is IS upon VB, IS upon alpha times VB upon VT. Okay. Next, quickly write collector current. Just 1 or 2 minutes. Sorry. Collector current IC. The electrons which are swept up across, the electrons which are swept across the collector base depletion region constitute IC, collector current IC. How are they related? IC and VB. IC is IS times exponential of VB upon VT. Okay. And how are they related? IC and IE. Which is bigger current than the two? IC is alpha times IE from these two equations, right? So this is an important equation. Whatever I am putting inside the box, that is an important relation between them. What is individually and how are they related? And what is alpha called as? Alpha is called as, you will later understand this, common base current gain. And alpha is always less than 1. Last is what? Base current, right? Yeah? Or 2 minutes. ठीक है. इतना ही है. Yes. हाँ. Base current IB consists of, last statement please students. IB consists of two components, IB1 and IB2. Yes or no? I think we have written the description of IB1 and IB2. Now can you write it down again over here? And IB is actually combination of both IB1 plus IB2. How it is related to IC? This IB, how it is related to IC? IC upon beta. Write down the relation. So how will you write this? IB. What is IC given by? IS times exponential of VB upon VT, right? This is IC. And if you divide by beta, you will get IB. Got it? And what is beta called as? Again current gain, but this is called as common emitter current gain. Common emitter current gain. And this is always greater than 1. Very much greater than 1. Okay. And at last, how are they three related? The three currents. IE is IB plus IC. These are called as terminal currents in BJT. Terminal current in BJT. And what is the relation in the exam? We can ask you, derive the relationship between alpha and beta. I think we have derived for alpha and beta today, right? How are they related? Alpha is beta upon 1 plus beta. If I want to prove other way around, then beta will be alpha upon 1 minus alpha. So this you prove it on your own. This I left as an exercise for you all to do it. So next time when we meet, we will start with the input output characteristics in different operating modes. Input output characteristics in different configurations of BJT. All right.